Alright, hey guys, what's going on? So today we're going to be talking about, again, curves. We're going to be talking specifically about the Frenet frame, or the Frenet frame. I don't know if I'm pronouncing that right, but we're going to be talking, in the last video we talked a little bit about these vectors, the binormal vector, the principal normal, and the tangent vector. We're going to be relating them to each other now a little bit more in depth. And then soon after this, we're going to start talking about geodesics. So with that being said, make sure to hit that like and subscribe button if you like this kind of content. Make sure to go onto my Patreon page as well if you want to support the channel. Anyways, let's get right into the topic. Alright, so in the last video we started talking about these three principal vectors that describe a curve. Okay, so we have some curve here. We can call the curve C. Okay, the curve C has three principal vectors that are associated with it at every point along the curve. So we have one is the tangent vector. So if C describes the position of some particle, say, in space, then the derivative is going of the particle, or the derivative of the position of the particle is going to be a velocity. And that derivative is represented by the tangent vector. Okay. The tangent vector, again, this gives us the velocity of a particle because it's the change in the position with respect to time, okay? And that change in calculus and in other courses, as you know, is associated with the tangent vector at that point. Okay, and then we have a principal normal vector. So the principal normal vector is going to tell us something about how the tangent vector changes. So that's sort of the second derivative, if you will, of the position, okay? And that is going to tell something about the force that a particle experiences as it's traveling along a curve. And we talked about that earlier as well. So we have a tangent vector, we have a principal normal vector, then we have this new vector that we're going to talk about a little bit in this video, which is the binormal vector. So the binormal vector, this is going to tell us something a little bit about the torsion that a particle experiences as it's traveling along a curve. Okay? And we're going to investigate this a little bit more in depth in this video. So, let's start. The tangent vector, we said, was the derivative of position with respect to some parameter. In physics, that parameter is time. Okay? But we're just going to call it some arbitrary parameter s. Okay? And we are going to say that some scalar multiple of n is going to be equal to the derivative of the tangent with respect to the parameter. Okay, so the n is really, it's like an acceleration, right? It's the double derivative of d of the position vector, right? Because if t is this, then this is the same thing as d ds times dr ds, which is equal to d squared r ds. All right, so that is the double derivative of the position with respect to the parameter. B is a binormal vector. So the binormal vector is going to be the cross product of the normal and the tangent. So the normal vector and the tangent are orthogonal to each other. And when we take the cross product of them, we're going to find that the binormal is also the binormal vector is also orthogonal, right? So I'll clean those up, actually. Those did not look good. So the binormal vector is orthogonal to these two vectors. Okay. So that's what we're saying right here. So dB ds, we can take the derivative of both sides of the equation by the parameter, because we want to get an understanding of what dB ds is. Well, that's going to be this, okay? We can expand this out, Okay, and we get this. Okay, and then we see if we multiply, let's see here. So this here we said was this up here, right? So this is just a normal cross with the normal. Well, that's going to be 0. Okay, because any vector cross product with itself is going to be 0. And then we have this right here. So the change in B in the binormal vector tells us something about the cross product between the tangent and the change in the normal vector. Okay. So this is some vector, right? This is a vector, and it's orthogonal to t, right? Because this is a cross product. It's the result of some cross product with t, so that means it's orthogonal to t. And given that this here holds, this is something that you probably learned this in calculus, maybe in a special relativity course. But given this equals 0, then dB ds is also going to be orthogonal to b. Right? So if it's orthogonal to t, right? So if it's orthogonal to t, okay, and it's also orthogonal. So if it's orthogonal to t and also orthogonal to b, right? So here's b. Then it has to be along the direction of the principal normal, right? So therefore, dB ds is parallel to the principal normal vector, right? And I also want to just mention really quick that this here holds because if we look up here, we have t dr ds, and then n is going to be the derivative. We can actually just look at this, right? So t dr by ds, right? That's this vector. Then the derivative of t is n, which is this vector, and they're orthogonal, right? So the derivative of some vector is going to be orthogonal to that vector, right? So that's this proposition of orthogonality, okay? Or that's this proposition right here. So, okay, so therefore, dB ds is parallel to n. This is the principal normal. And so by convention we put a negative sign here, and so therefore dB ds is going to be the some scalar multiple of n. Okay. So we have now that t is the RDS. Okay, this is the tangent vector. Kappa n is tdd or dt ds, and tau n is dB ds. So n, right? So n is actually the derivative. It represents the derivative of two vectors. It represents the change in two vectors, right? It's the change in the tangent and the change in the binormal. And these two scalars tell us something about how n represents the change in both of them. All right, where b again is the cross product between t and n. So we can encapsulate all of this. The change in t is equal to kappa n, and the change in b is equal to tau n. Right? So because we said by convention that this had to be negative. Okay, and we'll see why that works here. So why that convention works? Because if we can say the tangent vector is moving in this direction. We're going to call this the positive direction. And we'll say that this is the negative direction. So we could sort of think of this as, let me get my color. I'm doing purple. All right, so we can sort of think of sort of clockwise, counterclockwise rotation. And then here the tangent is going to be, this is going to be rotating as well, right? So this is why we have this minus convention, because again, you could just say this is a convention, but we use the minus this convention here to show that if this is changing in some direction, then this vector is going to change in some direction as well. Okay, and what we associate with this positive direction, we're going to associate this with a negative direction. All right, so this is just again by convention. So T and B are three principal vectors along a curve that define exactly what the curve, how the curve behaves, okay, or how the path sort of behaves, and they form a frame called the Frenet frame of a curve. And K is going to be the curvature of that curve, and T is going to be the torsion of that curve. A more compact way of looking at this is going to be like this, okay? So N, the change in N, if we come back up here, the change in N, right, so these are changes in TD and T and dB, or changes in T and B. The change in N, right, well that's just going to be the opposite of how these T and N's change, right? Because if we come back up to this picture, if T rotates this way, right, we can think of N rotating as well in some opposite direction, okay? And if B rotates this way, then N is also going to rotate this way. So we can sort of think of N as, let's see here, we could think of N, I get a green color out. We can think of N as it has the opportunity to move. I'll do it like this. It has the opportunity to move in sort of this direction, or it can move, this is kind of, I'm depicting this quite poorly, right? But it can move in this direction, right? So along the direction of B, that's what I'm trying to get at here. It can go, or it can move in this direction towards or away from T, right? So this is towards B or away from B. So this vector again, this N vector can rotate this towards B, or it can rotate in this plane as well. We have two planes, right? We have the plane. We have the plane that looks like this, the plane that N and T are in, and then we have the plane that N and B are in. And so N can rotate in this plane, or it can rotate in this plane. Okay. And that's what we're really saying here. So we're saying if T rotates, if T changes, it's going to change by rules of the N vector. And so the N vector is going to change in the opposite way, right? So coming back to this picture, I'm belaboring the point here, but coming back to this picture, if T rotates this way, then N is going to rotate, say it'll rotate this way. But if B rotates this way, then say N is going to rotate this way. So that's how we sort of compensate for everything up here. So that's why this here is going to be negative, and this is going to be positive. So we come to a very interesting look at things. T, N, and B transform. Here's T, the old T, N, and B's, and here's the new transformed T, N, and B. And so the matrix here contains the curvature and the torsion. And the curvature and the torsion, this is a symmetric matrix with zeros along the diagonal here. Okay? And this tells us, again, this matrix tells us if we have a curve, and we have or we have our vectors, and then purple, and then purple. Here's our B vector. This is our T vector, and then our N vector looks like this. Okay, well, if T rotates downwards, then something's going to happen to the N vector, right? So the N vector, say, if T rotates downwards, the N vector, say, will move, it's going to move in, say, this direction. Again, I'm not really drawing this out very well. Here, I'll do this. We have this plane. I'll draw it out a little bit better. We have this plane, and then we have this plane. Right, so if T moves down, so say T moves down, well, so that means that N is going to move along this frame with B. It's going to move because it has to remain orthogonal. So it's going to have to move up or down if this is going to move down. Okay. Likewise, if B moves, right, if B moves, then N is going to have to move within this plane right here, so everything stays orthogonal. The key of the game here is to keep everything staying orthogonal, and the way these things transform is defined by curvature and torsion. So we note it's anti-symmetric, has zero trace to it. Its determinant is also going to be 0, right? Because the only non-zero term here, we're going to get the curvature times the determinant of minus k 0 tau 0, right? Because I'm taking this times the matrix that these two guys form. That has to be a minus sign, but we see here automatically this is going to be 0, right? Because this times this is 0, this times this is 0. So this whole thing. So the determinant of this matrix goes to 0. The determinant of this matrix goes to 0. The trace is 0, but it's anti-symmetric. Okay. So this is the Frenet frame. This matrix describes the motion of the Frenet frame. Okay. The frame, again, is this picture right here. Okay. And this is some shorthand notation as well. Also notice that these are vectors within vectors, right? So T is a vector, N is a vector, B is a vector. So in 3 dimensions, this is actually going to be like if you flesh this whole thing out in 3 dimensions, this is going to be, if this is a vector, this vector, this is a vector, there's 3 of them, each one of them has 3 components in 3 dimensions, and that means this is going to be actually a 9-component vector. Okay, what that means here is going to be interesting. We'll talk about that later, because this is going to have to be a 9 by 9 matrix. And then we have these guys right here as well. But that's something for later as well. But anyways, we have talked about the Frenet frame. We've talked about how the Frenet frame moves along a curve. And yeah, so in the next video, we will talk about a little bit more of this, but we're going to quickly get into geodesics. So with that being said, I hope you guys like this kind of content. Make sure to hit again to hit that like and subscribe button. visit my Patreon page if you want to support the channel, and I will see you guys in the next video.